Imagine you're a 911 dispatcher, right? And you are trying to route an ambulance to a really critical emergency.
High stakes, yeah.
Exactly. So your software calculates the absolute fastest path. The driver hits the gas, and then suddenly they're staring at a solid concrete wall right where an intersection is, supposed to be.
Oh, wow. Yeah, that is a nightmare scenario.
Right. Because on the dispatcher screen, those two roads look like they crossed perfectly. But deep down inside the database, their digital geometries didn't actually connect.
Ah, right. The invisible architecture.
Yes, there was this microscopic gap, like a fraction of a millimeter wide, completely invisible to the naked eye, but massive enough to just completely break the routing algorithm.
Because the computer doesn't know what a road is, it only knows the geometry.
Exactly. When you are modeling the real world, a digital map is not just a pretty picture. It is a relentlessly strict, incredibly complex architecture of invisible rules. And if you are gearing up for the GISP exam, the GIS professional certification mastering, that invisible architecture is exactly what you need to do.
Yeah, specifically section 202, right? The spatial data relationships section.
That's the one. That is our mission for today's deep dive. We are taking a stack of study materials and extracting the absolute must-know concepts for you. Because, it's the difference between just drawing shapes in a graphics program and actually engineering a true geographic information system.
Well, yeah, in a standard graphics program, a line is just cluster of pixels on a screen.
Just color.
Right, just color. But in a GIS, that line has a mathematical relationship to literally everything around it.
Right.
It has behaviors, it has tabular data attached to it,
Wow.
and it has these strict, rigid rules governing what it's even allowed to touch.
Which brings us to the foundation of all of this. Before we get into the weeds, we have to start with Tobler's first law of geography.
Oh, the classic.
It is the bedrock. Everything is related to everything else, but near things are more related than distant things.
It sounds so poetic, doesn't it?
It really does. It sounds like, a piece of philosophical poetry rather than a strict database rule.
What's fascinating here is that this seemingly philosophical observation, it actually dictates the entire engineering framework of a spatial database.
Wait, really? How so?
Because things that are physically close to each other in the real world interact more. Right. So they require far more complex digital rules to govern their interactions in our software.
Okay, I think I see what you mean.
Like, if two properties share a physical fence line, their digital representations cannot just act independently. If one boundary moves, the other one mathematically has to respond.
Ah, so Tobler's law is essentially the justification for why we have to build these super rigid, interconnected data structures in the first place.
Exactly. It's why the database has to care about proximity.
Okay, let's unpack this. Because before we even get into the physical geometry, like how digital objects interact on the screen, we really have to talk about the spreadsheets.
The tabular data, yes.
Yeah, we need to understand the tabular connections hidden in the background that give these shapes their actual identity.
That is the perfect starting point, honestly. Because the geometry is useless without the tabular data. A point is just a point until the table tells you it's a hospital.
Right. And in relational database architecture, there's a specific mechanism that allows a GIS to associate an object in one table with a completely different object in another table.
The key.
Yes, the key. So let's say I'm picturing a massive utility grid, right? If you have a feature class, a distinct layer in your geodatabase that contains the physical location of every single utility pole in a city.
Okay, so that is your origin class.
Right, origin class. And visually, it's just a map covered in thousands of little dots.
But every single one of those dots has a row in the attribute table. And a specific column in that table serves as the primary key.
Usually that's the FID, right? The feature ID.
Yeah, exactly. Or an object ID. It is a completely unique identifier. So pole number 102 has a primary key that no other pole in the entire city possesses.
Okay, but the utility company also has a completely separate feature class representing electrical transformers.
Right, the destination class.
Yeah, the destination class. The problem is they are two totally separate lists in the database. How does the GIS mathematically prove which transformer is physically bolted to which pole?
Well, the database engine handles this through what's called a foreign key.
Okay, break that down for me.
The transformer feature class, the destination, will contain a designated column. Let's say it's called polide, and that column stores the exact same unique identifier found in the pole class.
Ah, so the foreign key in the destination class looks backward to match the primary key in the origin class.
Precisely. By bridging that primary key to the foreign key, the GIS software can just run a query, and instantaneously recognize, oh, transformers 305, 308, and 311 are all attached to pole 102.
That is so elegant. And once that bridge is established, the software allows you to leverage two very distinct but temporary operations.
Joins and relates.
Yes. And for anyone listening who is taking the GISP exam, understanding the mechanical difference between a join and a relate is absolutely vital. You will be tested on this.
100%. It's a fundamental concept.
So I always try to think about the processing cost on the computer's memory here. Let's start with the relate. We are usually dealing with a one-to-many scenario, right?
Generally, yes.
Say I have a point feature representing a restaurant, and I have an external non-spatial table containing like 500 user reviews for that one restaurant.
Right.
I absolutely do not want to force my map document to physically append 500 paragraphs of text onto that single restaurant point.
Yeah.
It would just bottleneck the entire system.
Oh, it would completely bloat the attribute table. It would crash your session.
Yeah.
This actually raises a really important question about database normalization. How do we access data without duplicating it all over the place?
And a relate solves that, right?
Really, it solves this by acting purely as a navigational pointer.
A pointer, okay.
The database engine basically says, hey, I acknowledge the relationship through the key, but I'm not moving any actual data. When you click the restaurant on the map, the software merely opens a window to the external review table.
It's essentially just a hyperlink.
That's a great way to think about it.
You click the restaurant, the hyperlink takes you to the reviews, but the actual text of those 500 reviews is never downloaded into your primary map document.
Exactly. It keeps things lightweight. But a join, on the other hand, operates with a much heavier footprint.
Right, because a join commands the database engine to temporarily merge the external data directly into your feature class's attribute table.
For the duration of that specific map session, yes.
Let's use an example. Say I have a feature class of the U.S. states, just the geometric polygons.
That's the shapes.
Just the shapes. But I also have this massive Excel spreadsheet I downloaded from some government website, and it has the latest election results.
Okay.
I can't just relate that data if I want to actually change the visual symbology of my map, right? Like, to make the state polygons turn red or blue based on the votes, the GIS software needs that data sitting physically inside its own attribute table.
Right. The rendering engine needs direct access to the values, so you execute a join.
The database engine dynamically appends the election spreadsheet to the state polygons in your computer's RAM.
Yes. And your map can now read the voting numbers as if they were native geographic data.
Yeah.
You can run your symbology algorithms, label the states with the winning candidate, whatever you need.
But the crucial mechanic you have to remember for the exam here is volatility.
Yes, the temporary nature of it.
Because it is happening in the RAM, not on the hard drive. I always say it's like using a sticky note to slap the election results onto a paper map so you can color it in.
That's a fun analogy.
Right. It works perfectly in the moment, but the second you close the software or, fold up the paper map, that sticky note just falls off.
The operation is entirely temporary. And honestly, that's by design. It protects the integrity of the original source data by never permanently altering it.
But here's where it gets really interesting. Because if I am an engineer and I'm building a multi-million-dollar digital twin of a city's infrastructure, I cannot have my database forgetting how the transformers connect to the utility poles every time I shut my laptop down. I can't rely on temporary sticky notes in RAM.
No, absolutely not. You need persistence.
Persistence.
And to achieve persistence in a real enterprise environment, we have to transition away from temporary joins and relates, and we start using formal relationship classes.
Okay, relationship classes.
A relationship class is not a temporary action executed in RAM. It is a permanent, distinct object stored explicitly inside the actual architecture of the geodatabase itself.
It is hard-coded into the system.
Yes, exactly. It lives in the geodatabase. And because it operates at the database level rather than just the map document level, it can enforce incredibly sophisticated behaviors.
Like what?
Well, the most critical distinction you need to understand, and this is definitely on the exam, is how it handles the life cycle of the data. We categorize these as simple relationships versus composite relationships.
Okay, let's look at the mechanics of a simple relationship first. This is where the destination object maintains its own independent existence, even if the origin object is completely destroyed.
Right. So think of retail mapping. Your origin feature class contains the physical building polygons for grocery stores across the state.
Just the building footprints.
Right. And your destination is a standalone table of corporate brand entities. Brands like, Target, Walmart, Safeway.
Okay, so If a specific target location in my town goes out of business, I'm going to go into the map and delete that building polygon.
Naturally.
But the database engine needs to be smart enough to realize that deleting the physical building shouldn't trigger a deletion of the word target from my corporate brand table.
Exactly. The brand target still exists globally, even if that one local origin point was destroyed.
The relationship is simple. They are associated, but their lifespans are totally independent.
Exactly. Now, a composite relationship, however, introduces a mechanic known as a cascading delete.
Ooh, cascading delete. That sounds intense.
It is. In a composite model, the destination object cannot logically exist without the origin object.
A university campus is a really great way to visualize this, I think.
Oh yeah, go ahead.
So the origin feature class is this massive polygon representing the official boundary of the university campus. And the destination feature class contains all the individual, smaller academic buildings sitting inside that boundary.
Right.
So what happens if the university goes bankrupt, the land is sold, and the campus is rezoned? I delete the main campus polygon.
The database engine instantly recognizes the composite rule.
Right.
And it executes a cascading delete. It automatically wipes out every single academic building associated with that campus in one go.
Wow. Just cleans it all out.
It has to.
Huh?
It prevents orphan data. You don't want buildings just floating in digital space with no parent entity that corrupts your database.
That makes perfect sense for, like, data hygiene. But from an architectural standpoint, I have to ask, how does the database engine handle the sheer volume of these connections?
What do you mean?
Well, it's easy to manage a one-to-one relationship, right? Like a single state having a single governor. But a state polygon contains thousands of retail stores, and a retail brand exists in dozens of states. How does this system not just get hopelessly tangled in the math?
It manages it through a structural property called cardinality.
Cardinality, another big exam term.
Huge term. Cardinality defines the numerical parameters of the relationship. As you said, a database engine handles a one-to-one relationship state to governor very cleanly.
Very simple.
It also handles one-to-many quite efficiently, like one state relating to a list of its many congressional representatives.
Right. And the inverse is true for many to one, right? Like hundreds of distinct counties all relating back up to one parent state.
Exactly. But the computational heavy lifting really comes into play with many-to-many relationships.
This is your retail store scenario. Target has branches in many states, and each state contains many different brands like Target, Macy's, Walmart.
Right. Relational databases inherently struggle with many-to-many connections. If you try to make a direct link, it creates this exponential, unmanageable web of foreign keys.
It would just crash.
It would. So to resolve it, the geodatabase actually generates a hidden third table behind the scenes.
A junction table.
Yes, a junction table. It uses this hidden table to cross-reference the keys and maintain performance without breaking the system.
That is exactly the kind of under-the-hood mechanic that separates a basic map maker from a true GIS professional. You have to know what the engine is doing when you ask it to connect complex data sets.
Absolutely. And, we have only been discussing the tabular data so far.
Right, just the alphanumeric characters stored in rows and columns.
Which brings us back to Tobler's law and the physical reality of the map.
The geometry?
Which link the geometry. The shapes themselves have to follow a set of laws, which introduces us to what is arguably the most intimidating yet elegant concept in spatial data.
Topology.
Topology, yes.
It sounds so complex, but it's really just the mathematical study of how point, line, and polygon features share geometry, right?
That's all it is. It is the framework that guarantees spatial integrity. And there's a super counterintuitive mechanic here that you absolutely must grasp for the GISP exam.
Okay, what is it?
Applying strict topological rules actually reduces the overall file size of your geodatabase.
See, that feels completely backward to me. You assume that adding a massive list of complex spatial rules to a database would make it heavier and slower.
You would assume so, yeah. But topology relies on something called coordinate sharing.
Okay.
Without topology, if you draw the border between, say, Colorado and Wyoming, you are forcing the database to store the exact same string of coordinate vertices twice.
Wait, twice?
Yeah. Once for the northern edge of Colorado and once for the southern edge of Wyoming. The database is literally drawing two distinct lines and just stacking them on top of each other.
Oh, so the computer's doing double the work to render the exact same visual border.
Exactly. But topology changes the math. It allows the geodatabase to store that sequence of vertices only a single time.
So Colorado and Wyoming both just reference that single shared boundary line.
Yes. It drastically reduces the coordinate storage requirements while simultaneously guaranteeing that the two states will never accidentally overlap or pull apart and leave a sliver.
That is brilliant. And to make those guarantees, the database utilizes a really specific vocabulary of topological relationships. Instead of just saying things are, near each other, the GIS analyzes the exact geometric intersection.
Right, the spatial algorithms evaluate the matrices of these shapes. Does this house point fall completely within the interior of the parcel polygon?
Does the driveway line intersect the interior of the road, or does it merely touch the boundary without crossing it?
Exactly. If a pipeline passes straight through a county, the algorithm classifies that as crosses.
And if a building footprint accidentally sits on two different zoning parcels, it overlaps.
Right. And if we connect this to the bigger picture, the software uses these classifications to enforce actual geodatabase topology rules.
Rules that we set.
Yes. These are strict, pre-programmed mandates that you impose on your feature classes to prevent spatial corruption.
I always picture these rules as like a fiercely strict jigsaw puzzle supervisor.
I love that.
Just pacing around the database, clipboard in hand, screaming at the geometry. Like if we're dealing with a polygon feature class, say property parcels, the supervisor's rules are non-negotiable. Polygons must not overlap, and polygons must not have gaps.
Because in the real world, property boundaries don't overlap. And there isn't just a mysterious void of unowned space between two adjacent houses in a subdivision.
Right. The database must reflect physical reality.
But the rules for lines are where the mechanics get incredibly sophisticated.
Oh, yeah. If I'm drawing a road network, I have to deal with dangles.
Dangles are tricky. A dangle occurs when a line segment abruptly terminates without snapping to another feature.
So in a road network, a dangle essentially represents a dead end.
Right. And sometimes that is completely accurate, like a cul-de-sac.
Sure.
But if you accidentally draw a major highway segment that stops just 1 millimeter short of connecting to the next segment, you have created an erroneous dangle.
Which brings us to the cluster tolerance rule. This is so cool. How does the software handle a line that is drawn a millimeter short by a sloppy user? It doesn't just leave it there, does it?
No, it doesn't. The cluster tolerance is an algorithmic distance threshold.
Okay.
If the vertices of two different lines fall within that microscopic tolerance radius, the algorithm treats them as coincident.
It essentially acts as a magnetic field.
That's exactly it. It recalculates the coordinates and just snaps the two vertices perfectly together, eliminating the gap and fixing the topology.
It forces the geometry to be clean. And it also monitors for things like pseudonodes. I was actually really fascinated by the mechanical implications of a pseudonode when reading the sources, especially for hydrologic analysis.
Oh yeah, a pseudonode is basically an unnecessary vertex that artificially breaks a single continuous line into two separate segments.
But why does that matter? Like, if it visually looks like a continuous river on the screen, why does the software care if there's a hidden node breaking the line segment in half?
Because analytical routing algorithms do not look at the screen. They read the node matrices.
Okay, right.
When a hydrologic algorithm calculates the flow of water down a river, it measures the computational cost of moving from one node to the next.
Wow.
Every node implies a potential intersection, a change in flow rate, or some kind of transition. An unexpected pseudonode forces the algorithm to halt, recalculate the cost matrix, and figure out what to do next.
Wow. So it introduces massive computational inefficiencies.
Worse than that, it can completely break the flow directionality of the network model.
It just fails.
Exactly.
So what does this all mean for us? We have our primary and foreign keys linking our tabular data. We have our relationship classes protecting against orphaned records. We have our cluster tolerances and topology rules ensuring our geometry is mathematically flawless. When all of this invisible clockwork is perfectly tuned, what high-level operations does it actually allow us to execute?
It allows you to run advanced analytical operations with total confidence in your output.
Yeah.
For example, you can execute a spatial join, which is a fundamentally different operation than the tabular joins we discussed earlier.
Right, because earlier we relied on a matching ID number, like the pole ID. A spatial join doesn't care about the ID number at all, does it?
Not even a little bit. A spatial join merges attribute data based entirely on geometric location. The algorithm just evaluates the topological relationship.
Give me an example of that.
Okay, if you have a massive data set of individual census points representing households, right? You can spatially join that to a polygon layer of voting districts. The algorithm simply checks the within topology rule for every single point. And if a household point physically falls within the boundary of District 4, It automatically appends the District 4 attribute data to that household.
That is incredible. It is deriving brand new information simply from the physical proximity of the shapes.
It really is. And you also unlock the ability to utilize geometric networks. A network dataset like roads or electrical grids relies completely on the perfection of your line topology.
Right.
If your topology rules fail and you have a dangle, a GPS routing algorithm will read that as a literal break in the physical road and will refuse to route an ambulance through it.
Back to our 911 dispatcher from the beginning.
Exactly. And finally, a perfectly clean database allows for collocation analysis. This is pattern recognition at its finest.
Collocation analysis.
It mathematically quantifies how often specific features occur in close proximity to one another.
So you aren't just looking at the map visually. You are running statistical models on spatial associations.
Right. It evaluates the exact adjacency and contiguity of features. Like, do specific categories of property crime statistically overlap with specific types of urban infrastructure?
Or are certain environmental risk factors collocated with dense population centers?
Exactly. You are finding relationships that aren't obvious just by looking.
It allows you to see the invisible forces shaping an environment. Wow. We have covered a truly massive amount of architectural ground today.
We really have.
Let's do a quick vocab fire just to make sure you are fully prepped for the exam,
Okay.
because they love to test you on the subtle differences in these terms.
Good idea.
Adjacency means sharing a boundary or touching. Contiguity is being connected or sharing a border. Continuity is actually physically touching. Overlap is occupying the exact same space. And proximity is just how close features are to each other.
Memorize those subtle differences.
Absolutely. So we started today with the philosophy of Tobler's law, which forced us to understand how tabular data is managed through keys. We looked at the processing differences between temporary joins and relates versus permanent relationship classes.
And how database engines handle those cascading deletes.
Right. And then we explored the mathematical coordinate sharing of topology, the strict enforcement rules that eliminate gaps and dangles, and how that clean geometry powers spatial joins and complex network routing.
And look, if you are studying for the GISP, knowing these mechanics inside and out is non-negotiable.
It is the core of the test.
But beyond the exam, mastering these concepts is really about recognizing the immense responsibility of building a digital twin of reality.
The real world doesn't have topological errors.
No, it doesn't. Rivers do not have unexplainable gaps in their flow. Utility poles do not just magically forget which transformers they are holding up.
The digital model has to be exactly as resilient as the physical reality it represents.
Well said.
Which brings us back to that 911 dispatcher. I want to leave you with a scenario to ponder on your own, involving those hydrologic pseudonodes and dangles we explored earlier.
Okay, let's hear it.
Imagine you are the GIS engineer tasked with modeling a coastal city's emergency flood response plan. You are mapping out exactly where millions of gallons of storm surge will flow when the levees break.
High stakes again.
Right. Now, if your cluster tolerance algorithm is configured improperly, and your digital elevation lines fail to snap together, what happens?
Oh, man.
How might a fraction of a millimeter gap in a topological rule, a gap that is completely invisible to the mayor looking at your printed map, how might that lead to a massive, devastating miscalculation of where the floodwaters will actually go during a real crisis?
The invisible architecture always dictates the real-world outcome.
Think about that. Keep digging into those database mechanics, and we will catch you on the next deep dive.